What I want to look at here is quite complicated. Well, even the reflection I think is quite complicated if you really understand it. It's something called refraction. Now, we say that light travels in straight lines. And we've got a special big word for that called rectilinear propagation. Cool. But it doesn't always do that. We all know that we get these funny effects with light and water, and we all know that's probably caused by refraction, but refraction is actually quite hard to understand. So let me try and explain it to you and point out the things you have to do in your explanations. Again, it's a level 1 thing, but if you've you've probably had it explained in science, but let's call this air and let's call this water, or glass if you like. Now, we always talk about those in terms of their optical density, and that's because light can travel through them, but it doesn't travel at the same speed. Air, for all intents and purposes, is a vacuum. So we're going to have something called a refractive index, which I'll explain a bit later, but the refractive index for air is virtually 1. Water, the refractive index, the optical density is a bit bigger, and we give it an optical density of 1.33. What happens is, with a more optically dense medium, as the light ray hits, it slows down. Now remember, the light ray has a wavelength. That's our wavelength. Normally we just draw the light ray like this, right? But I'm drawing the wavefronts because that's an important thing to consider. I'll draw my normal like that, perpendicular to where the wave hits. Now I know that when it goes more dense, the wave is going to bend towards the normal. Something you need to know. Less dense to dense, wave bends towards the normal. But why? And it's this. The wave front has a width. Now, this wave at this point has been traveling just through air, this part of the wavefront. But the other part over here had to travel through water. And so it slowed down and got behind this bit, and so it bent. So this part, same thing happened here and here. So what happens is this part's only traveled through air, but this part has had to travel a bit through water and slows down. So part of the wavefront slows down, part of it keeps going. And so we get a bending. The wavelength gets shorter in the water. Frequency stays the same, so the wavelength decreased. Frequency is the same. And this is because the velocity equals wavelength times frequency. If frequency is the same and the wavelength has got smaller, then the velocity is less. And the angle, we always measure the angle. Angle of incidence is the angle between the direction of the wave and the normal. So that's angle of refraction. Has got smaller. And we can actually calculate this. But let's just continue with our discussion. So why did the frequency stay the same? And that's because whatever is generating these waves determines how many waves are being produced. So even if these waves start to really travel slowly, let's give you an example. I'll use another bit of paper. We've got a whole bunch of waves being produced. They've been produced for millions of years, if you like. But over here, they reach into a medium where they travel more slowly. So they're all going slightly less than they were over here. They were traveling. This is the same amount of time, but these ones travel further, so their velocity is bigger. But from a frequency point of view, if I'm just standing near and seeing how many pass me in a given time, it's going to be the same over here. So frequency is the same. Wavelength is smaller in a more optically dense medium. Now, we can calculate all these angles, but let's first, before we do that, discuss something called refractive index. Refractive index tells us how optically dense the substance is and therefore how much the light slows down. So if you've got a velocity in air and you want to know how much it slows down in glass, then you just divide the velocity in air by the refractive index of glass, which is 3 times 10 to the 8 is the velocity in air, divide by 1.5, and we end up with the velocity in glass being 2 times 10 to the 8 meters per second. So it's very easy to calculate the new velocity. You just divide by the refractive index. Same with wavelength. If you want to know the wavelength in glass, you just take the wavelength in air and you divide it by the refractive index of glass. So refractive index tells you how much the wavelength changes and how much it slows down. And we end up with some formulas that you get given, which are like this. And these you should remember. They're basically saying that the refractive index in the second medium divided by the refractive index in the first medium is equal to the velocity in the first medium divided by the velocity in the second medium, which is equal to the wavelength in the first medium and the wavelength in the second. The way I remember these is the velocities go together, v1, wavelength 1, v2, wavelength 2, and the refractive index is around the other way. So you can use those formulas for a certain number of problems. And we've got another formula called Snell's law. N1 sine theta 1 equals N2 sine theta 2, which tells us all the maths we need to know for calculating the angles. So going back to this first part here, if we've got theta 1 and we want to know theta r, if we call this the first side and this the second side, then N1 is the refractive index on that side, N2 is the refractive index on that side, which with water was 1.3. Now we can just do these calculations to figure out the angle. So Snell figured this all out, and hopefully you'll have done a practical where you do that. Now, what happens when you go the other way is when you actually go the other way, where you're going from water to air, then if that's your incident ray, theta I, then the ray is going to speed up and bend away from the normal. So going from dense to less dense, it bends away from the normal. And this is going to produce a very interesting effect called total internal reflection. But I'll do a different video on that one. So in explaining refraction, you have to explain that it goes from one optical density to another, that changes the speed, and the critical part is this. You won't get a bending if the wavelength hits straight on. So the wavelength actually has to hit, or the wave front has to hit at an angle. So it's like this. If this is air and this is water, and my wave fronts hit like that, yeah, they're gonna get smaller, but they're not gonna bend because the wave front's hitting evenly. So you have to actually have the wave fronts, right, hitting at an angle to get this whole bending effect. So it's important to understand that. I think that's enough for our